Okay, let me just briefly repeat it. So, okay. So the first seminar in this semester. Oh, really? Oh, sorry. Maybe I was traveling. Oh, okay. Oh, yeah. You are. Oh, I'm sorry. Okay. It's nice to do this again because I made a mistake. Okay, so this is a second seminar in the semester. So today's speaker is Dr. Xiaojian Du from Galician Institute from in Spain. So he got PhD in Texas A&M in 2019 with Ralph Rupp, Professor Ralph Rupp, and he moved to Germany, and now he's working in Spain. So he will tell us universality of energy momentum response in conformal kinetics. Okay, please.
Thanks, everyone. So first, I would say sorry that this picture is inverted somehow. So I'm going to talk about the universality of energy response in conformal kinetic theories, and this is mainly based on some calculation and simulation for Quark-Gluon Plasma physics. So there are several philosophies in physics. One of the philosophy that actually for physics is history of strong interaction with matter that we have always think about reduction violent. So when we think about matter, we can think about finer and finer structure with higher and higher sort of experiments to find these finer structures like molecule or atom, nucleus, quark, and gluons, or even strings. So to the reductionism, this kind of philosophy for sort of strong interaction matter, I want to talk about the history, quantum thermodynamics. Back to the years of 1970, Brozak and Polymer defined symplectic freedom, which is 2004 Nobel Prize in physics. So this is the quantum thermodynamic language. So what this symplectic freedom is stating about is the running coupling becomes weaker at larger exchange momenta. And in this sense, once we have higher and higher experiment at higher and higher energy, we may expect larger exchange momenta between particles interacting. So we may expect there's weaker coupling and the confinement and new degrees of freedom in addition to the hadron, which is free gluon and quark, and a bunch of free gluon and quark are called Quark-Gluon Plasma. And another philosophy in physics is sort of emergence, which is talked a lot by condensed matter physicists. So scale of emergence in nature, there's one famous word can sort of describe this. More is different. So if we think about sort of microscopic state, like different species of birds, starting a sparrow, of course they have different features. But a flock of birds show possibly very universal collective behavior. Dynamics of these flocks of birds are very different from the dynamics of these single birds. This is sort of macroscopic things or collective behavior. And scales of emergence in quantum many-body physics, one thing that people talk about a lot, and also sort of from the microscopic physics to macroscopic physics, is that every quantum field theory is expected to have some hydrodynamic limit, which is sort of the emergence of these quantum fields. And when we also talk about the breakdown of this emergence from hydrodynamic states in quantum field theory inversely. So when we ask a few questions like, is there any universality in emergence, and how this breakdown microscopic theory first? So one of the emergence, which is sort of one of the potential objects in high energy physics, is the emergence of the QCD, quantum Gluon dynamics. There is some sort of experiment to create such kind of emergent behavior of free gluon and quark, which is heavy ion collision experiments with this Quark-Gluon Plasma. And there are several facilities in the world currently to do this heavy ion collisions. One is in the CERN, this HC, The other one is Rick and Kevin. So PD has a word for this sort of heavy ion collision, like 核子动对撞生金态. So then you smack two very heavy neutrons and to very high speed, close to the speed of light, and collide them, and this kind of collision makes new kind of states, which is this Quark-Gluon Plasma. And here I show sort of the picture of different stages to heavy ion collision experiments. Start with sort of initial collision, which is highly non-equilibrium, and you have, and then those two neutrons traverse with each other. There's a big field flux, which is described by classical field theory, and the patternize of this sort of field create this particle, gluon and quark. It's also a non-equilibrium sort of kinetic theory to describe it. Then we can talk about the hydrodynamic state eventually after the thermalization of this non-equilibrium QGP, which is sort of emergence of QCD. And from experiments of heavy ion collision, people already see some collective behavior, which is an indication of hydrodynamic states of this QCD plasma. So this is the emergence of the QCD in heavy ion collision. So how do we start from sort of QCD to hydrodynamic theory? So we start from QCD. The first step to sort of take the problem towards collective behavior emergence is to sort of construct a QCD effective kinetic theory, which is state of the art to study this non-equilibrium Quark-Gluon plasma. And this theory is effective theory of two-point correlation QCD. So this is QCD Lagrange. The basic degrees of freedom is sort of the let's see, the field for fermion, for boson, and also these quantum states. But once you calculate those sort of, let's say, two-point correlations, this basically represents the physics of the density of bunch particles. And if we talk about basic degrees of freedom, this is density, we can write down sort of this effective theory, which is a set of coupled Boltzmann equation, and for gluon and quark distributions. So this is the set of coupled Boltzmann equation, which is a basic equation for this QCD effective kinetic theory. And this distribution represents a distribution for quark and gluon. This is a collision integral, which represents an interaction from basic QCD calculation. And this collision integral, including two parts of the information. One part of the information is part of the interaction. You have a sort of scattering amplitudes. So here are several channels, basically 2 to 2 and 2, which is called elastic and inelastic radiation. Another feature from this QCD is the quantum statistics. You have sort of a statistical factor. You have both enhancement spectra and fermion blocking factor in these collision terms. So this is another level, sort of already sort of emergence from QCD to sort of kinetic theory. Another level of emergence to make it more macroscopic is hydrodynamic theory. Right? So hydrodynamic theory is sort of macroscopic theory in a long wavelength frequency limit. What it means that you have typical scales of this sort of hydrodynamic theory. We see this kind of fluid dynamics every day from this kind of lake or river. You have this wave. And the typical scale is a long wavelength limit, means the mean free path of two particles, mean free path of a particle scattering in this kind of hydrodynamic fluid is much shorter than the typical length of this hydrodynamic state. And low frequency means the mean free time, the time for the particle to scatter between sort of two scatterings is also much shorter than the frequency of this wave moving hydrodynamic state. So in this sense, there's sort of fast interaction or thermalization, the moving of a wave, and one usually expects that hydrodynamic states are sort of close to equilibrium. Sort of can use this. So when we talk about the hydrodynamic state of QCD plasma, we can talk about the thermal state of gluon, thermal state of quark, which is sort of described by the Bose-Einstein distribution or Fermi-Dirac distribution, and have some sort of deviation from this thermal distribution. The main feature about these hydrodynamic modes, so one of the features is that there are small gradients. Of course, we have these kind of scales, and these gradients, if you do a Fourier transform, you have sort of have these K modes or wave modes, which just represents the gradients. And another feature about hydrodynamic modes, in some literature, is sort of a definition of hydrodynamic mode. Is that once the wave modes goes to zero, or gradients goes to zero, the frequency of this medium also vanish. So why hydrodynamic theory is important in relativistic heavy-ion collision? It provides a successful description of near equilibrium Quark-Gluon plasma that we showed in previous slides, that this lasts for the longest time for all these stages in heavy-ion collisions, and it provides a medium background for the hard particles, jets or heavy quarks and quark-gluon. So those particles in hydrodynamic states are Quark-Gluon plasma. Those are softer particles with low momentum. Those states are close to thermal states. And there are several sort of hard probes. We have very sort of separated scales compared to those softer modes. Those are, for instance, the jet, which is a high energetic particle with very large momentum, or heavy quark with very large mass. And all in all, they have very large energy compared to the soft QGP. And another important feature, which is also sort of hot topic in recent years of heavy-ion collision study, is energy deposition through the hydrodynamic medium from the hard probes as well, because we know once there's interaction, there's not just interaction from A to B, but there's also interaction from B to A. So there's medium modification to these hard probes, and there's also energy deposition to hydrodynamic medium from these hard modes. So when we talk about hydrodynamic modes, there's also non-hydrodynamic modes, which sort of modes, I mean, literally modes which is not hydrodynamic. So there are several examples of things which is not hydrodynamic. One of the examples is that we have discussed this equilibration of these jets in the equilibrium QGP, so sort of hard modes interaction with sort of QGP. Another sort of which is non-hydrodynamic is pre-equilibrium state in heavy-ion collision. So you have this initial collision, you have very far from equilibrium states, and we see the hydrodynamic states has sort of the particles close to equilibrium. But once we have initial collision which is non-equilibrium, we have to use kinetic theory, not hydrodynamics theory, to describe it. This also sort of catch the physics of non-hydrodynamics. And during this thermalization, there is so near equilibrium states you can discuss hydro, and finally equilibrium uses kind of ideal hydrodynamic theory. I will discuss the details about this later. And there are several features about non-hydrodynamic modes. So which first, for instance, a state with large gradients, and those K are not small, and non-vanishing frequency, which is also an indication of non-hydrodynamic modes. So how do we study these non-hydrodynamic modes? In principle, any correlator in quantum field theory out of hydrodynamic region can be used to study these non-hydrodynamic modes. And specifically, since we already sort of construct emergent theory, which is kinetic theory, QCD kinetic theory, which is sort of already simplified the QCD calculation. So especially the kinetic theory can also help us to understand this non-hydrodynamic modes. So how do we construct this sort of hydrodynamic theory from QCD kinetic theory, more emergence? So from kinetic theory to hydrodynamic fields. So once we have, so we know the basic degrees of freedom in kinetic theory is distributions of gluon quarks. We can sort of construct the hydrodynamic theory close to thermal equilibrium, so you can assume this distribution sort of thermal, close to thermal with small perturbations. Then you can do an integration over this momenta. You calculate those first order moments, which is sort of number current. If you use some charge, you get some charge current vector, and another quantity which is second order moment, which is just any tensor. And from hydrodynamic theory, one thing, sort of from conservation, from conservations, you can sort of construct hydrodynamic equation, this in terms of the hydrodynamic fields. So you sort of further simplify the equations we want to solve from kinetic theory to hydrodynamic theory, and specifically for the sort of ideal hydrodynamics of zero or in equilibrium hydrodynamics, one can easily construct those hydrodynamic fields with sort of tensor constructions in terms of the number density or velocity of the fluid, energy density, or pressure. And away from equilibrium, which is sort of the viscous correction, dissipation correction to the hydrodynamics theory, which is called viscous hydrodynamic theory. And the way to construct this hydrodynamic theory is that we sort of expand this energy moment tensor on track vector in terms of zeroth order, first order, second order, in terms of those orders. But those orders means that when constructing those tensors, we have those gradient expansion. And for first order, you have this sort of first order gradient expansion. For second order, you have second order gradient expansion. So the traditional way, standard way to construct hydrodynamic theory. And there are several models on the market for this hydrodynamic theory from these constructions. So the first order hydrodynamic theory is probably the most famous hydrodynamic theory, which is Navier-Stokes hydrodynamic theory. There are several second order hydrodynamic theory because when people construct these theories, they have different assumptions and criterion for construct different orders. I will not go into details of this. So a more closer way to look at the from kinetic equation to the hydrodynamic equation is that we can sort of linearize this effective kinetic theory and assuming some thermal background for the kinetic theory and use perturbation to represent the sort of the hydrodynamic fields away from thermal equilibrium, away from ideal case. So consider this effective kinetic theory. We can decompose this distribution into a spatially homogeneous background and an inhomogeneous perturbation. So this is a distribution in a homogeneous background, which is can assume it's thermal, and the inhomogeneous perturbation. For transform, we'll transfer this gradient sort of to this wave number k, which is convenient for the calculation, and it will result in a linearized effective kinetic theory with a number in terms of this number k, and equation for the background will vanish, so limited because the collision term will narrow, so the equation will be contributed. And one can still calculate the tensor and for the background and perturbation. So the background is ideal case and the perturbation is sort of viscous correction. And one can further calculate the response function in terms of time and wave number. The response function carries information about how this energy is transferring from one place to another place, one position to another position, which is sort of a ratio of angular tensor in terms of time evolution of angular tensor divided by its initial value. But of course, when we sort of construct this response function directly from QCD, one can also calculate some correlation functions. But this is a sort of simple way to calculate this from kinetic theory. Now we can consider some initial condition, which is scalar type perturbation, which is the simplest case with this sort of thermal background, which is, let's say, this is still fluid background, and the perturbation, which is temperature. So temperature perturbation. So we know that thermal distribution is depending on the temperature. So if we vary a little bit of the temperature, we have perturbation. And there are several modes or several types of response to this kind of different perturbations. So one of the simplest mode is sound channel. For this temperature perturbation, kind of scalar type perturbation, you only have this sound channel. But if you have this velocity perturbation, you also have some shear channel. And in this specific work, I will only talk about this sound channel. And I can also tell you that there's also a lot of other channels that they are not independent to each other. We can also find some relationships, but I will not go into details. So before I jump into the most detailed simulations of these response functions from kinetic theory, I'll talk a little bit about universal scales, which is sort of can simplify our discussions. So we know that response functions in terms of time and wave number. So here G is the response function, T and K. And different interaction strengths will give different relaxation time. And we know that relaxation time is less proportional to the eta over f, which is the viscous correction of transport coefficients. First coefficient, viscous coefficient in the hydrodynamic theory. And one can sort of define a rescaled or dimensionless time and wave number this way. And one typical value for in terms of this, the T bar and K bar, which is universal time and the wave number. And one of the important number value for this T bar is that when T bar is equal to 4 pi, which is basically the hydrodynamic time, which is from logical studies, we know this kind of time. And now we can sort of transfer this response function in terms of T and K to this universal T bar and K bar. And one can also rewrite the response function from hydrodynamic theory in terms of this T bar and K bar. So typically, for the first order hydrodynamic response function, one can sort of find some analytical solution for this response function, which has two terms, including a cosine term, which is presenting this sort of oscillation, this wave and decay modes, which is representing the damping the hydrodynamic modes. And if we rewrite this response function in terms of T bar and K bar, one can universally representing this response function, and with Cs, which is speed of sound, which is just a constant, and without other sort of coefficients this way. Yeah. So in this sense, the Cs is just a constant. Okay. So we sort of test and study universality among different kinetic theories. So for kinetic theory, I just talked about the kinetic theory sort of in a very brief way. But there are several kinetic theories from sort of different assumption or different quantum field theory. So for instance, the simplest kinetic theory is called relaxation time approximation. So you have you can assume some sort of form for this collision integral, which is just distribution minus the equilibrium distribution, thermal distribution. So once the state of distribution approaches to equilibrium limit, the collision integral becomes 0, and there's no further sort of interaction. It becomes thermal. So this is a very basic idea of all these kinetic theories. So other kinetic theories are similar, but from sort of directly from field theories. For instance, the simplest sort of kinetic theory from field theory is 5-4 scalar theory. You have this kind of very simple scattering channel. And another more involved theory is called Yang-Mills kinetic theory, which we were talking about the F23 Yang-Mills theory. We have several channels. So a typical channel which is sort of implemented on the market for these studies is this 2-2-2 elastic into Asian process. And of course, the ultimate interesting thing is the kinetic theory from QCD. We just discussed this QCD kinetic theory. So we have several kinetic theories from different quantitative theories, and QCD kinetic theory that we are only talking about is sort of most complicated. Okay, now let's see the response function we calculate from kinetic theory. So remember that we first calculate the angular momentum tensor from this integration of momenta of the distribution for Gluon and Quark, and then we can define this response function. So in this figure, I present the response function for first order hydro and different kinetic series, these 4 types of kinetic series, the comparison between them, and in terms of k times t, so k bar times t bar. So we sort of see this universality of all these kinetic series, and of course, this is the case at k bar very small, which means you have a very small gradient, which is basically the hydrodynamic limit, a long wavelength limit of all these kinetic series. So they're expected to actually converge to hydrodynamic limit at this small k. So what is new is that once we look at the response functions at slightly larger k, larger gradient, which is sort of away from hydrodynamic limits, although we see all these kinetic series are different from hydrodynamic series, this is expected because this is sort of hydrodynamic region. But all those kinetic series, they sort of still have a universality among them. The large k by at the early time, which is sort of also at the region, which is not. So one can also sort of take a more closer look at its response functions by fitting those response functions from the kinetic theory with several sort of dispersion relation and damping relation with some complex frequency. So we see the structure of this response function. You have sort of oscillation and some damping. So you can assume some response function form with some sort of vector with exponential decay and complex frequency, which is omega here with additional phase, which is a little bit arbitrary, but you have to do some fitting to get that. Okay, so in terminology, we want to define non-hydrodynamic modes as the modes before the hydrodynamization time, because this is the time when the hydrodynamization haven't finished typically. So we call this non-hydrodynamic modes. And once the for later time, for time later than the hydrodynamization time, we call it sound mode. And for the sound mode at small wave number, we call it hydrodynamic modes. So there are several remarks I want to make. Is that so if you look at this frequency, it's a complex frequency, and the negative frequency we also give the same mode as positive frequency, just with slightly different base factor. So we can call sound modes that can appear in pairs, and one may expect many or infinite numbers of non-hydrodynamic modes for those early time, not just a pair of modes. But in order to sort of extract those modes in a simplified way, we represent them with a single non-hydrodynamic fitting procedure. Then we can sort of extract this complex frequency. So here's an example of fitting QCD response function with different wave number. So we see in this figure, we see this kinetic theory is purple curve, and the sound mode is red curve and hydrodynamic curve. So we see this blue curve is basically vanishing, and sound mode actually dominates the kinetic theory curve. That means at a small k, sound mode dominates. This is also expected that at a small value, all those kinetic theory will converge to hydrodynamic theory, and sound mode will dominate. Non-hydrodynamics will not work. And if we increase a little bit of this wave number, we sort of see increase of this non-hydrogen modes, fraction of non-hydrogen modes, and the fraction of sound modes drop down a little bit. Just at a slightly larger wave number of gradient, we are a little bit away from hydrodynamic limit. That's why you see this non-hydrogen modes. If we further increase the wave number gradient, we see more non-hydrogen modes here at an early time, and there's competition between sound modes and non-hydrogen modes. And there's also sort of a deviation of the total sound plus non-hydrogen modes compared to the kinetic series, because we only use one single non-hydrogen modes to represent all non-hydrogen modes, which is a little bit realistic fitting procedure. And we further increase that. So we see at some point the non-hydrogen modes take over the dominance sound. So this blue curve is non-hydrogen modes, the red curve is sound mode. See, this actually is larger than sound mode, and this green one is summation of sound mode plus non-hydrogen modes, which is further away from the kinetic theory curve. So after extract those complex frequencies, we can also look at some sort of structure of these complex frequencies in a complex plane. So we know this complex frequency, it has two parts, the real part and the imaginary part. We can plot the real part, imaginary part, one complex plane to sort of represent those different poles for different theory. So those poles are different sound mode poles for different kinetic theory, scalar field theory and QCD. So they sort of have some divergence at the large k value, and they sort of merge at small k value, which is hydrodynamic limit. And in this figure, I also show two limits. One is the ideal hydrodynamic limit, just a very trivial value here, and another curve is first order hydrodynamic limit, which at eta over 1, just typical sort of the hydrodynamic theory can sort of reduce the kinetic theory of QCD with this coupling strengths we choose. And we can also look at those complex frequencies in terms of wave modes. So the left-hand side, I choose hydrogen modes. For the real part of hydrogen modes, basically the distribution relation between Yang-Miller's kinetic theory and QCD kinetic theory. And in the right-hand side, I choose the imaginary part of this complex frequency for Yang-Miller's and QCD theory. So there are some physics I want to deliver, sort of not so related to hydrogen, but sort of we can see this from those hydrogen. So we can sort of get to the effective eta over S for hydrodynamic theory, corresponding to these two types of kinetic theory. So for Yang-Miller theory, we find that so with the same terms of coupling of Yang-Miller theory and QCD theory, we extract the eta over S, the shear viscosity over entropy density ratio for Yang-Miller theory for second order hydrogen is 0.62, and for QCD it's 1. So what this means is what this eta over S means is if you have small eta over S, that means you have sort of effectively larger coupling or faster interaction of the theory, because once you have 0 eta over S, you recover the ideal hydrodynamic limit. The ideal hydrodynamic limit means you have very fast interaction of the medium. Ultimately, distribution particles instantaneously become thermal distribution. That's why in ideal hydrodynamic theory, you have thermal distribution for those states. So what it means that if we compare eta over S with succinct coupling for Yang-Miller QCD, you have smaller sort of eta over S for Yang-Miller theory compared to QCD. So that means Yang-Miller theory actually thermalizes faster than QCD. QCD thermalizes sort of slower than Yang-Miller theory. The reason is that the quarks in the QCD actually slow down the thermalization. This is due to the fact that quark has smaller degenerative factor, and quark has sort of quantum statistics, which is polyblocking, also suppress the interaction between all those particles channels involving quark. So this is sort of the figure I show. So this complex frequency in terms of k, which is not the universal k, but if we can sort of also rescale this wave mode to k bar, and well, after we rescale that, we can also compare different kinetic theory. So here, what I will show is that once we rescale that, we show some universality of all those kinetic theories, because this eta of S sort of basically represents the different speed of thermalization of this sort of series. After we rescale that, sort of makes it at the same speed of thermalization. So here I show those sort of real part of the complex frequency in terms of k bar for different kinetic theories, and compare to two types of hydrodynamic theory. One is ideal hydrodynamic theory, the other is second order hydrodynamic theory. So again, one of the relation we find is that at small wave number, all those kinetic theories will tend to sort of converge to the hydrodynamic limit. And away from small k value, at a large k value, of course, all those hydrodynamic theory, they will fail, and all those kinetics, and we can see that ideal hydro and second order hydro, they are vastly different from each other. They are also vastly different from all those kinetic theories, but we still show some universality of those kinetic theories, even at very large k. And we can also look at the imaginary part of this complex frequency represents a damping relation among kinetic theories. So the message is very similar. You have this hydrodynamic theory, which is being reproduced at small k, all the kinetic theories. But away from the hydrodynamic limit, cannot describe it, cannot have this hydrodynamic limit, but all the kinetic theories will still have some degrees of universality. And one can also look at the residue. The residue is the overall factor of this fitting function, the response function. This basically represents the different fractions of sound modes or non-hydrodynamic modes, because we use the response function for sound modes and non-hydrodynamic modes together to fit them. So here I show the residue for sound modes with different kinetic theory. So of course, at small k, sort of converge to the hydrodynamic limit, and sound modes will dominate. So the residue is close to 1. And of course, at large k, you sort of have non-hydrodynamic modes take over the dominance. So the sound mode residue become very small, but we still show some some degrees of universality of kinetic theories. One can also look at the response in position space among those kinetic theories. So we were talking about the response functions or dispersion relations in terms of wave modes. If we do an inverse Fourier transform back to the position space, we can also look at this response function in terms of position. So here I show still the free streaming solution, which is free gas limit, which is without any interaction. And the first order hydro is sort of the limit close to thermal, and those kinetic series curves. So we see that all these kinetic series actually still have some universality. This is at roughly early time, and the free streaming solution, because it has sort of free gas, so all those particles freely flying without any interaction, and because we are talking about conformal limit, sort of massless limit of those series, so all those particles are flying in the speed of light. So the peak of this free streaming solution is at 1, and first order hydro mode, the speed of this is sort of will be closer to the speed of sound of the conformal series. Of course, ideal hydro will be exactly at this speed. First order hydro is a little bit outdated, so somewhere between the speed of sound and speed of light. And if we move to a little bit later time, we see this sort of all those kinetic series still have some universality among them, and the curves between the first order hydro and the kinetic series, they become closer and closer, because at a later stage those particles will thermalize and closer to the thermal limit, which is also closer to the hydrodynamic limit. This is at sort of very late time, and we show this first order hydro and all kinetic series closer to each other. So all those things that make sense. And now another thing I want to talk about is sort of the things ongoing. So we know that sort of once you have a hard probe or jet traversing the soft Quark-Gluon plasma, the medium will modify the jet. The jet will also modify the medium. So this is a typical jet in an equilibrium, so QGP. So jet is a highly energetic parton. There's splitting of the particles into different small, so showering on jets, and those particles will further interact with those medium particles. So this is a typical picture of medium modification to jet, and of course those jet will also sort of modify the medium, which is called jet wake. So this is very similar to the situation when we have a boat voyaging lake. So you have sort of wave or energy depletion so behind this boat. This is the wake of the boat. So the typical way to sort of simulate this wake in a hydrodynamic theory, that you linearize this hydrodynamic theory in terms of the background and perturbation, and you can solve this hydrodynamic equation and solve for this equation for both the background and the perturbation, and the solution for this perturbative sort of hydrodynamic theory can help us construct the shapes or the wakes from this boat. So there are already some calculations based on this hydrodynamic theory on the market. So what we want to do is that sort of to construct some jet wake in the QCD kinetic theory with sort of non-equilibrium background away from the hydrodynamic limit. We can still have a background plus a perturbation, and perturbation sort of describe this kind of wake, and the background can describe this kind of non-equilibrium sort of Quark-Gluon plasma. This is sort of a new direction we are pushing. So more specifically, we can sort of linearize this kinetic theory in terms of background and perturbation, and we can calculate these response functions in terms of k wave modes, and this sort of we can also treat this response function in some sense universally, and we can use these response functions and do a sort of convolution of the position space and time to reconstruct the perturbative tensor or transparent vector to sort of construct this jet wake in a non-equilibrium background. So here's my summary. So what I expected and verified is that kinetic theory will converge to hydrodynamic limit at small wave number gradients, and there's linear response of kinetic theory can be described by sound mode plus nonhydrodynamics. And what are strikingly new from our simulation is that we find some universality of energy momentum response function among all those kinetic theories, which is true even at early time and at large group number, which are typically non-equilibrium region. And what our future perspective based on this work is that there's possibility to sort of push the hydrodynamic description to non-equilibrium region with sort of to doing some fitting to this kinetic theory universal response functions to construct hydrodynamic theory beyond the gradient expansion with some other form. These gradients are in terms of numbers, and this work can also help us to sort of simulate the jet wake in the non-equilibrium hydrodynamic background. Thank you.